Thank you, Phil. So I'm delighted to be here today, sort of in Bonn. It's morning in Berkeley, and Mark Twain supposedly once said that the coldest winter of his life was the summer he spent in San Francisco, and it's one of those days here. Okay, so my talk is about certain multilinear functionals and inequalities for them. And I won't read you this first slide. Most of you already know all this, but there are lots of applications, lots of places where multilinear functionals and inequalities arise. So here's what I'm actually interested in the box. So I have a multilinear form which acts on a tuple, a J tuple of functions. Functions fj. I have a ball in some Euclidean space, and in this talk, it will just be a ball in R2. Think of it as a small ball. I have a product with finitely many factors. I have functions composed with mappings. So the mappings are mappings from this ball that is from R2 down into R1. So each factor really depends only on one variable, but they're not necessarily coordinate variables. I have real analytic submersions, Vj, from R2 to R1. And so the level sets of each submersion define a foliation. So I have finitely many foliations of a ball in R2. You should think of these foliations as having pairwise transverse leaves. And for each foliation, I have one factor which is constant along the leaves of that foliation. Okay, so geometrically, it's a somewhat complicated situation. You can also think of this as an integral over a Cartesian product of the domains of the FJs, but we're integrating not over the whole Cartesian product, but only over a certain two-dimensional subvariety. Okay, and my goal is an inequality of the following type. So I want to majorize the absolute value of this scalar valued form by a product of norms of the factors. And the twist is I want to use negative order Sublevel norms. These are LP-based Sublevel norms, but you should really just think that P is infinity. I'm not going to be interested in precise exponents, and if you have P equals infinity, then you get other P's by interpolation. So the main thing is we want an estimate in terms of negative order Sublevel norms. Okay, so again, I've just rewritten here the goal. I want to majorize the form by a product of negative order Sublevel norms. And the first observation is that this isn't always true. In particular, such an inequality is false in the simplest case, which is where all the mappings, Vj, are linear. And the way you see that it's false is trivial. We introduce a large parameter, lambda, which will later go to plus infinity. And we just take each of our functions to be a simple exponential, e to the I times the parameter times lambda times x. The mappings Vj, we have three linearly independent mappings, let's say, in R2, so they're linearly dependent. So I can choose coefficients which are non-zero so that this linear combination vanishes identically. And then if I plug in these particular functions fj into this product, then what happens is that the exponents all sum up to 0. The integrand is identically 1. And so it certainly doesn't tend to 0 as lambda goes to infinity. But if the exponents aj are not 0, then these functions do tend to 0 as lambda goes to infinity in any negative order Sublevel norm. All right. So in the case where all the mappings are linear, the inequality I want is certainly false. Okay, now one can reformulate the goal in a way that doesn't mention negative order Sublevel norms. So here we assume some localization of the functions fj on the Fourier side. So I'm going to assume that at least one of the factors, one of the fj's, has a Fourier transform that's supported where the frequency variable c is large, greater than or equal to lambda. And in that case, all we're looking for is a bound in terms of L infinity norms with a negative power of lambda. Okay, so that's what we're looking for, a bound in terms of a negative power of lambda if the Fourier transform lives at high frequencies. Okay, And so this is why I call these implicitly oscillatory inequalities. By assuming that the Fourier transform is supported at high frequency, I'm assuming that there's some oscillation in the factor. Okay, so that explains the name. Okay, and there's a very simple conjecture here. The reasonable conjecture is that the kind of inequality we're interested in is true whenever it's not trivially false. This is somewhat in the spirit of the last talk, of course. The inequality is true whenever it's not trivially false. And trivially false means that there exist non-constant real analytic functions in some open set for which this sum vanishes identically. If you have such a thing, then again, you can form e to the I lambda g is fj, and then you'll get the same phenomenon. The integrand will be identically 1, and the negative order Sublevel norms will tend to 0. Okay, so this is the obvious obstruction, and the conjecture is that in the absence of the obvious obstruction, the inequality is true. Okay, now it's important here that we are dealing with real analytic data instead of C infinity data. In the case of C infinity data, you could have a situation where this identity holds not identically in an open set, but to infinite order at some point, and then the inequality would still fail. So I've chosen here to assume everything is real analytic in order to avoid the more technical assumptions that would be needed to extend the theory to the C infinity case. Okay, all right. So the conjecture is not only for integrals over balls in R2 with, but for integrals over balls in any space with any finite number of factors, provided that everything is real analytic and there's no obvious obstruction. Okay, why are we talking in the title about the quadrilinear case? It's just because the trilinear case has already been treated in prior work, and the quadrilinear case is the next step. All right, this kind of inequality has a sort of symmetry. The inequality that we're interested in is essentially invariant under changes of variables. You can make an arbitrary real analytic change of variables in the variable of integration x, so that in this case is in R2. But you can also make independent real analytic changes of variables in the domains of the factors fj. So we have a product of diffeomorphisms groups, which is a sort of symmetry group of the inequality. And thus you see that the obstruction is not just having linear mappings Fj, but rather having a tuple of mappings which is linearizable under this symmetry group. Okay, so here's the main theorem. It's theorem O for oscillatory, and it simply says that there exists a negative Sobolev exponent S, so that my form is majorized by a product of the negative order Sublevel norms in the case where we have exactly 4 factors and where we're integrating over a ball in R2. There has to be an assumption, and I've said that there are examples where this doesn't hold. And so I'm stating the theorem a little loosely here by simply saying that it holds for generic data. So for generic 4 tuples of real analytic mappings from R2 to R1, this holds. And I'll say a little bit more below about exactly, more precisely what I mean by generic. Okay, so for quadrilinear case, where we're integrating over a ball in R2, the conclusion holds under the under genericity assumptions. Okay, now this is well known to many of you, I'm sure, but the trilinear case is much simpler than the quadrilinear case. Suppose that we're integrating over a ball in R2 with coordinates x and y, and we have f1 of x, f2 of y, f3 of x plus y. That's a linear case, so my conclusion doesn't actually hold. But still, in that case, there's a very simple bound available. We can majorize the form by a product of an L2 norm of F1 and L2 norm of F2, and crucially, the sup norm of the Fourier transform of the third factor. Okay, so what that means is that either this sup norm is small, in which case the integral is small, or the factor F3 has a certain kind of structure, namely it has a large Fourier coefficient. But in the quadrilinear case, if you write the form out in terms of the Fourier variables, which is what you do to get this trilinear bound, in the quadrilinear case, you get an integral over R2 with 4 factors, each of which depends on a linear function of the 2 coordinates. You have just enough information from Plancherel to say that this integral converges absolutely, but there's no extra factor. So you can't get a bound of the sup norm of a Fourier transform. And as a result, you don't get any structure on any of the factors right away. And the proof breaks down from the very beginning. One can compare this with Roth's proof of Roth's theorem about arithmetic progressions of length 3 versus Symmetri's theorem for progressions of length 4 and higher. The same issue arises. Likewise, if you compare the bilinear Hilbert transform to the trilinear Hilbert transform, this same issue arises. So this is a very common point. Okay, so the quadrilinear case we expect to be more challenging, or at least more intricate than the trilinear case. Okay, the proof of the theorem, which I will try to outline in this talk, relies in part on the interplay between 2 kinds of inequalities, oscillatory inequalities and what I call sublevel inequalities. And so next I'll discuss a little bit sublevel inequalities. All right, so here's a formulation of sublevelset inequalities with variable coefficients, which is an issue that's going to come into the proof. So what we're given here are mappings. Again, they're mappings from a high dimensional Euclidean space to a lower dimensional Euclidean space. Again, I'm assuming that they're real analytic throughout the talk. And we're also given some matrix valued coefficients, AJ. So those are also assumed real analytic. And then if we have measurable functions defined on R little d, they're allowed to be vector valued as well. To a tuple of such functions, I can associate a sublevel set. So my sublevel set is a set of all points in my ball that's in the big dimensional space, where a linear combination of the functions fj composed with vj, so those are these functions that are constant along the leaves of certain foliations. They're vector valued functions, so I hit each of them with a variable matrix. I get vectors. I add up those vectors. I take the magnitude of the vectors, and I consider the set of all points where that magnitude is less than some parameter, epsilon. All right. So this set is defined by a system of a certain number of linear inequalities with smooth, even real analytic coefficients involving measurable functions of fewer than capital D variables. All right, and here, the kind of inequality we want is one which asserts that the measure of the sublevel set is majorized by a positive power of this tolerance epsilon. Okay, now there has to be a hypothesis here, because if all the fj's vanish identically, then the sum is identically 0 and the inequality holds everywhere. And likewise, if the functions fj are small, then the sum is trivially small everywhere. So this inequality cannot be true without some hypothesis. And we make the minimal hypothesis, which is that for at least one of the indices, k, the absolute value of the kth summand is greater than or equal to 1 at every point. Okay, and again, we understand that we're going to need some hypotheses here on the coefficients aj and on the mappings vj. But this is the goal. We want to majorize the measure of the sublevel set by a positive power of epsilon. And we want to do that under minimal hypotheses. We got to assume that one of the summands is large, but we don't really want to assume anything else. Okay, the basic scheme of the proof of the oscillatory inequality is to reduce it in part to sublevel inequalities, and several different sublevel inequalities actually come up in the analysis of the quadrilinear case. In today's lecture, I will outline how at least two of those sublevel inequalities arise. I'll talk about the steps that reduce to them. I won't have time probably to say anything at all about their proofs. All right. So again, I'm just reminding you of the setup. B is now a ball in R2. In my sublevel problem, I'm going to have 3 functions rather than 4. So J is an index that runs over 1, 2, 3. For each J, I have a nice real analytic submersion from R2 to R1. I have coefficient functions, which are scalar valued and real analytic. And then I have my sublevel set, where I form a sum of 3 terms, each one being a smooth variable coefficient, which you should think of as being given, times an unknown measurable function composed with Vj. I add those up, I take the absolute value. I want the sum to be less than epsilon. Okay, so that's the kind of sublevel set we're interested in. It's a 3-term variable coefficient inequality in a 2-dimensional ambient set. Okay, and here's the theorem. So the theorem says that there exists an exponent delta, which is positive, so that under appropriate hypotheses on the data, the coefficients and the mappings, there exists a constant, so that if I assume that one of the terms is always greater than or equal to 1, then indeed the measure of the sublevel set is majorized by a constant times the positive power of epsilon. Okay, so again, here I have 3 summands, and I'm going to use this to analyze the oscillatory inequality with 4 factors. Okay, and I need to tell you, of course, a little bit about the hypotheses. I've simply said that there are hypotheses, and I need to say something about what those hypotheses are. Okay, so here's the main hypothesis for Theorem S. S is for sublevel. So the hypothesis is that if I have real analytic functions fj, which satisfy the 3-term sum of aj of x, fj consolved with bj of x, vanishes identically in some non-empty open set, then all 3 functions must vanish identically. Okay, this is a necessary condition for the conclusion, obviously. If you have a solution to this, then you can multiply these by a large constant to make one of them greater than 1, and then your sublevel set is an open set. Its measure certainly isn't small. Okay, you might want me to express this hypothesis in some simpler terms, but to actually write it down in simpler terms is rather complicated. In the real analytic case, this is a natural way to formulate it. Okay, likewise, for the oscillatory theorem, our hypothesis is that any real analytic solution of this 4-fold sum vanishing identically in any open set, here the hypothesis is that any solution is constant. Okay, notice that here we do not have variable coefficients. Here we have constant coefficients only. Okay, and that's the main hypothesis for the oscillatory theorem, but there are some other hypotheses. Okay, more about the main hypothesis. How would you actually verify it in practice? So this is the one for the sublevel problem, the 3-term version. How would you show that there are no solutions, no smooth solutions, except the obvious one where all the 3 things are 0? Well, you would assume that this equation holds in an open set, and you would differentiate it. If you differentiate it, then you get more equations. In fact, we're in a 2-dimensional domain, so you have 2 coordinates. You can differentiate in 2 different directions, so you can produce 2 additional equations, and you can keep going and get a very large, perhaps, set of equations. Now, the fj's are functions of a single real variable. if you differentiate n times with respect to the two-dimensional variable x, you get roughly a constant times n squared different equations. If you think in terms of Taylor expansion up to some order capital N, the Taylor expansion of fj up to order n involves only capital N coefficients. So if you do this process, you take all derivatives up to order capital N, look at Taylor series at some point, you have roughly capital N squared equations, and you have roughly 3n unknowns. So you have a good chance of eventually getting more equations than unknowns, and thus you can hope to show that the fj's must vanish identically in order for this thing to hold. Okay, and for instance, you can use that reasoning to show that for generic data in the sense of jets of Taylor expansions up to some large enough order, the main hypothesis really is satisfied generically in a natural sense. Okay. There are also auxiliary hypotheses, and I'll just state the main auxiliary hypothesis for the sublevel theorem. Suppose I have an index which is in the set 1, 2, 3. Remember, this is a 3-term setup. Choose a vector field, a real analytic vector field, which kills phi sub k. So that's going to kill any function composed with phi sub k. Okay. Another hypothesis is that if we have real analytic functions gj, which satisfy this equation, which you sort of get by applying vk to the threefold sum, if this vanishes identically in some Muppet set, then the functions gj must also vanish identically there. Okay, and I assume this for each choice of k. So this is 3 hypotheses. This expression here on the left is not what you get by applying the vector field v sub k to the threefold sum. If you apply v sub k to the sum, each term in the sum is a product of the coefficient aj times gj composed of phi j, and I get 6 terms, and I get 4 terms. And anyway, I have simply dropped some of the terms here. So this is not a consequence. This is not exactly the same as a differentiated version of the main hypothesis. And it turns out I need this, at least in the present version of the proof. So this hypothesis also holds for generic data in a reasonable sense. I don't know whether it's necessary, but what I do know is that if the main hypothesis fails and the auxiliary hypothesis fails, then things are really quite bad. And there are other kinds of counterexamples besides the trivial ones that come from the failure of the main hypothesis. There are other counterexamples that have multi-scale structure. So this hypothesis, it's not clear whether it's necessary, but it's certainly relevant. Okay, and then I have minor supplementary hypotheses. In the present version of the theory, I want to assume that all the coefficients vanish nowhere. I want to assume that the gradients of the mappings phi j are pairwise linearly independent. Most likely, and almost surely, these hypotheses can be weakened. We really want to assume that the coefficients aj don't vanish identically. We want to assume that no 2 of these are linearly independent everywhere, etc. All right. So I hope that most of the supplementary hypotheses can be removed, and my student Ziria Joe has some progress in this direction on some special cases of these problems. Okay. At any rate, there does exist a capital K, so that all the hypotheses hold. If you fix the point, choose a sufficiently small ball center at that point. If the Taylor expansions of the aj and the phi j's at a point lie in the Taylor expansions up to order capital K lie in a certain Zariski open set, then all the hypotheses do hold in a small neighborhood at that point. So everything holds generically, at least. Okay. There are some prior results in this direction. The first one I know of is due to Bourgain in 1988. He proved a trilinear inequality of this oscillatory type for three specific mappings: phi of xy equals x, equals x plus y, and equals x plus y squared. And of course, we saw this basic example just 2 weeks ago in the lecture of Heuristic. And so Bourgain used an inequality to prove the existence of triples x comma x plus y comma x plus y squared in subsets of the reals of positive Lagrange measure in a certain quantitative way. In a very different direction, there was a paper of Joly, Métivier, and Rauch in 1995, motivated by considerations coming from partial differential equations. So what they were interested in was weak convergence of products of this type. You have a threefold product of mappings, Fj composed of Pj. You have a sequence of Fj's, Fj comma nu. You assume that as nu goes to infinity, the factor Fj comma nu tends weakly to some limit. And what they wanted to conclude was that the threefold product in L2 also converges weakly to some limit. And they proved that if phi satisfies an appropriate form of the same main hypothesis. And they pointed out, of course, that if all the mappings Fj are simultaneously linear, then this weak convergence fails to hold. Okay, now what's interesting is that their proof didn't prove any inequality. It was a proof by contradiction. They used a machinery called microlocal defect measures, and they obtained no quantitative form at all. So they didn't obtain a bound in terms of negative order Sublevel norms. In principle, they showed that there's some non-trivial inequality, but they weren't able to say exactly what it was. Okay, and again, their work was motivated by considerations involving nonlinear PDE, although as far as I understand it, there were no actual direct applications to PDE. Okay, more recently, I proved a trilinear version of today's main theorem. So you have an integral over a ball in R2, you have mappings composed of Fj's. The Fj's are analytic and satisfy the transversality hypothesis. And there's an inequality with negative order Sublevel norms. Subsequently, Durchik and Roos and I treated a slightly different setup where we're integrating over a ball in R3, and we had three very specific mappings. But again, we had the same kind of bound involving some negative order Sublevel norms. As I'll try to explain, if I don't run out of time, this joint paper established one of the main elements in the proof of today's main theorem as well. Okay, there is also closely related work that goes into the work that Mariusz Mirek told us about 2 weeks ago, the work of Mirek and Krause and Tao, and subsequent work with other authors. So I won't say very much about how all this is related. Okay, so results like this oscillatory theorem, the main theorem of today's talk, is mainly envisioned as a sort of engine that goes into various applications. So for instance, Durchik and Roos and I used something like this to prove upper bounds for multilinear maximal functions and singular integrals. Okay, in this slide, I try to explain heuristically what the connection is between oscillatory inequalities with products and sublevel inequalities with sums. So I'm going to consider the unimodular case. We have this oscillatory expression where each factor is a pure exponential e to the I, Fj composed of Fj, and of course the Fs are real valued. Okay, and so I'm going to assume that the Fs are very smooth. So it's, this is just heuristic. So you apply the stationary phase method, which says that an integral of a product like this the integral is small unless the gradient of the total exponent is not very large. So more precisely, we expect that this integral should be small unless the gradient of this sum is not small on a set which is reasonably big. Okay, and now I'm not going to exploit the full gradient. Instead, I'm going to exploit one component of the gradient. So let's define V sub 4 to be a nice analytic vector field which annihilates phi sub 4. And I'll just consider the V sub 4 component of this quantity. So as a result, the term that involves phi sub 4 gets killed, and I get a sum with only 3 terms. When you apply the vector field to this composition, of course, out comes by the chain rule, out come certain factors. So we get variable coefficients, and now we have a sum of functions composed with the phi j's. And now the functions gj that arise are the derivatives of the original functions. So again, this is going to be purely heuristic. I can't quite do this in the measurable case. All right. Originally, I had a hypothesis that one of my 4 factors has a Fourier transform which is supported at high frequencies. And what that should mean is this: if e to the I f k hat is supported at large values of the variable, then it should be that the derivative of f sub k has magnitude roughly the size of the support of the Fourier variable. So the functions that arise in the sublevel problem are roughly derivatives of the logarithms of the original functions. And the Fourier localization hypothesis that I start with becomes a largeness hypothesis on one of the summands here, which, as we've seen, is exactly what we should need for a sublevel set bound. Okay, now to get things into the right situation, what I should do is divide through by lambda. So one of my summands, instead of being large, is simply greater than 1. And then as a result, the bound that I have for the sum should involve a negative power of lambda. So that's what gives me the small parameter on the right-hand side. And if I get a bound in terms of a power of that small parameter, that's really a bound in terms of power of the original lambda. Okay, so this is the heuristic reduction of the oscillatory inequality to the sublevel inequality. And roughly, the proof goes by trying to make this heuristic, work. So a large part of the proof of the oscillatory theorem is a justification of this heuristic. In particular, we have to, in a meaningful way, differentiate functions that are merely measurable. Okay, the heuristic converts an oscillatory inequality to an additive sublevel inequality. Things get a little more complicated because you pick up variable coefficients from the chain rule, as we've seen, but there's an advantage, which is you drop one index. So if we start with a quadrilinear expression and do this kind of reduction, we can hope to reduce to a sublevel inequality with 3 terms. And of course, that's an enormous gain in enormous simplification if we can drop one factor. Okay. On the other hand, the presence of the variable coefficients is a complication. Okay, so now I'm going to start by trying to explain in a rather gross outline how the reduction goes. So I'm going to assume that all my functions are in L infinity and have L infinity norms bounded by 1. So I want to bound in terms of a negative power of the parameter lambda. Okay, I'm going to assume that each of my functions is lambda band limited. So the Fourier transform is supported where the frequency is at most a constant times lambda. And I'm also going to assume that one factor is supported where the Fourier variable has magnitude at least a small constant times lambda. And by the usual kind of decomposition of the Fourier space and lumping terms together properly, you can reduce to a sum over lambdas, which are powers of 2 of these situations. Okay, now we take our domain of integration, which is in R2, and we cut it up into cubes of a certain size. the side length of the cubes is a certain negative power of lambda. And just like the last speaker, but for less good reasons, I'm using the exponent, I'm using the parameter lambda to the -3/4. In this talk, any exponent strictly between 1/2 and 1 works. They're all equally good. I'm not going for optimization. So there's nothing special about 3/4 in this talk. Okay, I can also change variables. I can exploit the symmetry group so that one of my mappings maps x1 comma x2 to x1. All right, so I've cut the problem up into subproblems, each of which lives on a cube of length lambda to the -3/4. And then on each cube, we can use the Cauchy-Schwarz inequality to eliminate one factor. So I have some trilinear expression paired with F4. I can use Cauchy-Schwarz to majorize things by the L2 norm of F4 times the L2 norm of a certain quadratic expression. So here's what you get. You get fixing the cube. I have a variable x, and I have a new variable, which I'm going to write as x plus 0 comma s, where s is a real parameter. Now, I'm working in a cube of side length lambda to the minus gamma. And so any 2 points within that cube are within roughly lambda to the minus gamma of one another. So this new parameter s is not a macroscopic parameter, but it varies over an interval I, whose length is roughly lambda to the minus gamma. Okay, so for each cube q, we get an integral over a 3-dimensional domain. So I have a new coordinate that ultimately is a good thing. And I have a product of only 3 factors. That's also a good thing. But each of my factors is now itself a product of 2 factors. So now I really have a 6-fold product in the integrand. And that's not what I want. So what we're going to do is we're going to view each 2-fold product as a single factor. So I have a sum over all the small cubes. For each small cube, I have an integral over an extra variable. I have also the integral over the cube, and I have a 3-fold product with 2-fold factor, with factors that are 2-fold products. So I'm going to define capital F sub j to be a product of 2 little f sub j's. The exact definition is down here in this box. So capital F sub j of y is f sub j of y plus f times f sub j complex conjugate of y. And that depends on this extra parameter s. So I put that in the superscript here, but I want to think of this primarily as a function still of the single variable y. Okay, so I have a sum over all these small cubes. I have an integral for each cube over a 3-fold, 3-dimensional small region. And I now have a product with 3 factors, each of which is still composed of phi j, but now we have this extra parameter s floating around. There's a factor in the exponent which depends on the cube. So this c sub j is a certain thing. It doesn't matter what it is, but it's a certain function evaluated at the center of q, and it does vary smoothly from one cube to another. So the different parameters are interacting, the different s's are interacting with the x variables. You can't separate them out. Okay, but the main thing is that the quadrilinear form has now been reduced to trilinear forms, which is certainly a gain. Okay, so we have a large sum of local trilinear forms, and we want to deal with those. So here we use Fourier analysis. So for each parameter s, I have this capital Fj. It's a function of a single variable y, and I expand it in local Fourier series with respect to y. So on intervals of side length lambda to the minus gamma, capital F sub j is a sum of Fourier coefficients, which I'm calling A, times characters. The characters have frequencies that are integers, and they're scaled by the appropriate factor of lambda to the gamma. And the Fourier coefficients depend also on the extra variable s. So all the s dependence is here in the coefficients. Okay, and I have a sum over all integers k. Okay, and I do such a Fourier series for each interval in the domain of capital F j at the scale lambda to the minus gamma. Okay, now each cube in the two-dimensional domain corresponds to an essentially unique ordered triple of intervals in the domains of the functions capital Fj, just via the mappings Tj. And essentially unique means there's a bounded number of 3 tuples for each cube. All right. So I can plug each of these Fourier expansions in to the threefold product that I'm integrating, and I get a big sum of threefold products of characters. And so for the integral of a product of 3 characters, well, there's just a trivial bound, and we just write it down. It's essentially 0 unless the frequencies kj satisfy certain relations. And then we can exploit Bessel's inequality. The Fourier coefficients, I'm expanding bounded functions in Fourier series, so I have little L2 type bounds of the Fourier coefficients, and we can plug those bounds in, and we can conclude that the contribution of a cube Q is majorized by an integral with respect to the extra parameter S of a threefold product of powers of L infinity norms of the coefficients. So this is the same device that occurred when I explained why the trilinear case is simpler than the quadrilinear case. You can majorize things in terms of L infinity norms of Fourier coefficients. And here I've just done it 3 times and taken a geometric mean to get the 1/3 power of the L infinity norm of each factor. Okay, so that is the basic trilinear bound which we want to exploit. And now we're into the realm of sort of standard arguments from additive combinatorics. So I want to decompose each of my, this should be a capital F, not a little f. I want to decompose each capital F into a pseudo-random part, all of whose local Fourier coefficients are small in the sense that they're majorized by a certain negative power of lambda, plus a sum of Fourier monomials, things where I have coefficients that are not small, but there can be only a certain number of terms where the Fourier coefficients are large. The number of such terms is O of lambda to the 2 sigma. And so I get a sum of a relatively small number of Fourier monomials. Okay, and so the combination of stationary phase and Bessel's inequality gives me a sum for the contributions of all the pseudo-random parts, which is a negative power of lambda. So there we simply won. One just has to deal with the structured parts. Okay, so sigma is an exponent, and I haven't told you what it is. We just choose sigma to be a small positive exponent. We gain here a certain small negative power of lambda. And what's left is simply the construction of the contribution of all the structured parts. If sigma is small, the number of structured parts is growing like a positive power of lambda, but it's a small positive power. And I hope to win a better negative power to counterbalance this loss of a positive power. Okay, and so indeed, I have 3 factors. So I lose a factor of lambda to 6 sigma. That's not so bad. But modulo that factor, we reduce matters to the situation in which each of the capital F's is a Fourier monomial. It's a single Fourier character times a bounded coefficient on each interval of length lambda to the minus gamma in its domain. So the domain is cut now into these very short intervals. On each interval, my factor capital Fj is relatively simply behaved, but there are many of these small intervals, and I have no control on how the frequency varies from one interval to another. So it's still a complicated situation. All right, so now capital F sub j, it depends on this parameter S, and it's a sum over all these short intervals of indicator functions of the intervals times constants, but the constants depend on the parameter S in some unknown way. And then I have Fourier characters but the characters have frequencies which depend on S in some unknown way. Okay, so the dependence on S is still very, very bad here. Okay, so again, you put those into the local trilinear form, and you conclude by stationary phase that the resulting integral is small, unless the total phase is nearly stationary, which is something which has to do with the gradients of the phi j's, and there's some linear relation which involves all these unknown Fourier frequencies. Okay, so this is still a somewhat complicated situation. Okay, now I want to think of these frequencies as really a function of a continuous variable. They define functions of y and s that are piecewise constant on intervals of a certain length with respect to y, but these intervals are so short that the local constancy isn't going to help me much. So I want to think of these Fourier frequencies now as being functions. They are essentially unknown functions of two variables, the spatial variable y and the extra variable s, which we added in when we did Cauchy-Schwarz. Okay, so I can interpret this relation here, the stationarity relation, as defining a sublevel problem. And so I have a sum with three terms. I have these unknowns gj. They're evaluated at a certain place, and let's not worry about the exact formula. There's a new function psi that comes in here. So it's a function of y and also a function of y times s. These functions gj are scalar valued, but they're multiplied by the R2 valued functions gradient of phi j. So I have an inequality with two components. And I have a sublevel set defined by this being big O of 1. And I want to prove that the measure of the set where that happens is controlled by a negative power of lambda. So that's a sublevel set problem. I don't have a small parameter on the right-hand side, but what I do have, as I already explained in the heuristic discussion, is that one of the GJs has to be very large. It has to have order of magnitude roughly lambda. So I can divide out by that and have a small parameter on the right-hand side here. So I have a sublevel problem of exactly the kind that I described. Okay. All right, so I really just already explained this. You can't hope to have a good bound for a sublevel problem unless you know that the individual terms on the left are reasonably large. But we should know that, after all, because we started with a largeness hypothesis on the Fourier support of one of the factors. But that Fourier support hypothesis applied to the little f's, and the capital F's are defined by multiplying together two little f's. And it could be that when you do that, you multiply two things with high frequency, and the frequency, the net frequencies, things could cancel, and you could get a low frequency product. So the argument that I have shown you thus far doesn't go through as it stands. This argument breaks down if the capital F functions are built largely out of slowly oscillating terms. So the argument breaks down if the functions capital F with the parameter s as functions of y are slowly oscillating for many parameters s. Okay. So proposition, the sublevel bound does hold. This is, again, a theorem about a sublevel inequality. So this sublevel bound that we get does hold, provided that one of the functions gj is suitably large. Okay. So what remains is to handle the case where when we multiply two of the little fj's together, the rapid oscillation, which we're initially assuming to be present, cancels, leaving us something slowly oscillating. Okay, so really everything I've said so far, except the last proposition, which is a sublevel inequality, is more or less the obvious adaptation of the existing trilinear analysis to the quadrilinear case. You do Cauchy-Schwarz to eliminate one of the factors, which is the obvious thing for all harmonic analysts. And then you just try to go as far as you can with the existing trilinear analysis. But here's where you get stuck. Okay, you get stuck because two of the little f's could multiply together and the rapid oscillation could cancel. Okay, so the next step that's needed to get around this was taken in my joint work with Durchik and Roos. So we established a structural decomposition. A general function can be decomposed as a sum of two parts in such a way that for one part, when you multiply two factors together in the way that we had to, the resulting function capital F is still built out of things that are rapidly oscillating with respect to the variable y. Okay. The other part is itself a sum of a small number of structured parts. So we're gaining structure. And so the flat term is handled by the argument that I've already outlined. And matter's now reduced to the case in which each of the fj's is of the other kind, which it turns out means the following, that little f can be expressed as a sum over these short intervals, capital J. These are still the lambda to the minus gamma intervals. I'm working separately within each such interval. On that interval, we have a constant coefficient, which depends on the interval. And then we have, again, a Fourier monomial, a single character. We have a frequency about which we don't know very much. It varies wildly from one interval to another, but we have a single character on each interval. Okay, so the difference now is that I have this property for the original factors little f, not for the capital F that are derived from them by multiplying two together, but in this part, I have that property for the original little f's. Okay, and so the proof has now boiled down really to the heuristic situation I told you about at the beginning, where each factor locally has a relatively simple oscillatory structure, but I don't know how that structure varies from one short interval to another. Okay, so I'm now back to the quadrilinear oscillatory situation. I'm assuming that each of my little fj's is a sum over short intervals of constant coefficients, which are uniformly bounded, times Fourier monomials. And I want to think of these frequencies, which are constant on each short interval, rather as defining a function of a continuous variable, which is piecewise constant. Okay, all right. So now we can apply stationary phase again. We're doing it to a fourfold product integrated over a two-dimensional domain. And again, things reduce to a sublevel type problem. I now have a sum with four terms. I have essentially unknown gj's composed with the original fj's, but now when I take derivatives to do stationary phase, I also get the gradient of each mapping Fj, and that is an R2 value term. So I now have a fourfold sum. It takes values in R2. So I have a system, I have a sublevel set, which is defined by a system of two inequalities. And we just do the obvious thing. We use one of the two inequalities to eliminate one of the four functions. So the result is a scalar inequality. Oops, sorry about that. The result is a scalar inequality with three terms. I have coefficients aj, which come from the gradient of the fj's. So they're not arbitrary, but they're related to the fj's. And I have a sublevel inequality. Here I have a large quantity on the right-hand side, not a small quantity. And on the right-hand side, I want the measure to be controlled by a negative power of lambda. Although I've mentioned it several times, I have not used the main hypothesis in my setup, I'm assuming that one of my functions has a Fourier transform that's supported at high frequency. And I have the whole argument so far has not used that in any way. So that's got to come in. All right. So here's I've just rewritten the definition of the sublevel set that we have. We want the measure of that sublevel set to be controlled by a negative power of the parameter lambda. And I'm reminding you now that at the very outset, we arranged that at least one of my f's had a Fourier transform which is supported at high frequencies. That means that the g that was derived from it also is large. So one of my functions g sub k is pointwise large. And now the terms on the left-hand side are large, roughly of size lambda. The exponent gamma is strictly less than 1. So this becomes a non-trivial inequality. It says that I'm adding some things. I'm taking a linear combination of things, one of which has at least size lambda. I want that sum to be much smaller than at least the largest term. So that is in principle a non-trivial thing. We can hope to have a bound for the sublevel set. And indeed, we now use the second theorem that I stated, the sublevel theorem, which was exactly about this situation where I have a sublevel set defined by a sum with 3 terms and variable coefficients. Okay, so if you invoke that theorem, the proof is concluded. Okay, so I am out of time, as I expected to be. I don't have time to say much about the proof of the sublevel theorem. Until less than a week ago, I had a very complicated proof of that theorem, and I was planning to spend most of today explaining that proof. But then I believe that I discovered a much simpler proof, which I, however, still need to verify carefully. So I'm suppressing the proof of that entirely. In both versions of the proof, though, there's the same overarching strategy. The main step is a regularity step. Given functions little fj, the functions capital Fj in this slide have nothing to do with the functions capital Fj in the earlier part of the lecture. I'm sorry about that. So we're given functions little fj in our sublevel problem. And what we want to show is that up to the epsilon in the sublevel problem, they agree with much better functions. So on a set whose measure is bound to be low by at least the positive power of the measure of the given sublevel set, we want to show that little fj agrees up to O of epsilon with a very regular function. So a very regular function is, first of all, real analytic, but second, it lies in a compact family in a reasonable sense of real analytic functions. So we have not just differentiability, we have some kind of uniform bounds on the derivatives. Okay, and once you can get to that situation, it's enough to analyze the sublevel set that's defined by these very regular functions, capital Fj. And that's a very standard thing, which all harmonic analysts know. If you have a reasonably smooth function, if you have a lower bound on some partial derivative of that very smooth function, then you get a lower bound on the measure of the associated sublevel set. Okay? So the main step here is to establish some sort of regularity, is to show that the functions in the sublevel problem really can be approximated by much better functions. And I'm going to stop there. I don't have time to say anything more about that. Okay, so thank you very much for your attention.